It's a great pleasure for me to introduce the next speaker, Professor Ulrike Lohmann from the ETH in Zurich. So she studied meteorology in Mainz and Hamburg and did her PhD at the Max Planck Institute for Meteorology in Hamburg. After her PhD, she spent several years in Canada at Dalhousie University and also in Toronto, and had stations at Columbia University. And in 2004, she accepted the offer of the full professor for atmospheric physics at the Institute of Atmosphere and Climate at the ETH. The research of Ulrike focuses on cloud physics, ice nucleation, aerosol processes, and in particular aerosol-cloud interaction, understanding how clouds form, and involves climate modeling. The research of Ulrike is awarded with several awards. She holds an ERC's advanced grant. She's an IPCC lead author, is member of the National Academy of Sciences Leopoldina, an HU fellow, and I could mention a longer list, but I would like to hand over to you, and we are looking forward to your presentation about clouds, their formation and importance for climate.
Yeah, thanks a lot. It's also my great honor to be here and talk to you. You will know topic-wise it's very different from what you've heard, especially yesterday. At least there's one connection to the previous speaker that at one point I will also be using AI, but not so much as you heard before. So I'd start with clouds. Actually, cloud physics, that's what I call my area of study, is complicated physics because it combines thermodynamics, statistics, radiative transfer, everything, you name it. But unfortunately, we don't have so nice labs set up as you guys if you do all of your studies somewhere inside. But the beauty of it, you can see them. You can see them, you can appreciate them, you can run away from them if you think it's downpouring on you. You can dream what you see in those clouds. You have all possibilities ahead of you, whatever you want. So what is it actually, if we think about clouds and weather, they are also related to lots of the extreme events that we have. As nice as you may like it, if it's like sunny day after day in summer, at one point it's not nice anymore. Then the cities become way too hot these days. The rivers run dry. So a lack of clouds means also a lack of precipitation. And on the other hand, of course, we have like flooding associated with if just it downpours like crazy, and that then creates environmental problems as well. So too few clouds is not good, and also not if they precipitate too severely. Maybe I should point where I want. So what is that I'm going to talk to you about? First, just starting with how actually are clouds formed, and then how are they affecting our current climate? After you have learned about that, then the logical question comes up, couldn't we use them to avoid some of the global change that we have and that we don't want, as I just showed you with droughts and floods? Well, first of all, how do we get there? There's, from the meteorological point of view, you distinguish it in between what's needed macroscopically. That is that you do need sufficient moisture in the atmosphere, and you need rising of air. Rising of air, if it's completely dry, doesn't help you, and just moisture sitting there and no rising and adiabatic expansion won't do anything to you either. So you need both of that. And then on the microscopic level, the tiny aerosol particles come into play. And if you want to know much more about them, then Bernadette is the person who can tell you all about them. For me, they are just the seeds that I need for the clouds. So, first thing is we do need some lifting. We get that in the atmosphere often enough just because we have frontal systems coming through. It's raining today, so you do have a frontal system. And whatever you have, it is the warm air rising above the cold air. It's a little more gentle if it's a warm front. So if you do have the warm air just gliding above the cold air, but it's a little more steep if you have a cold front where the cold air pushes from behind and really forces the air up, then you can also get some thunderstorms. Or, as you also have here, surrounding Vienna, some hills or some mountains, and then the air is also forced to go over. The most interesting ones, meteorologically, the ones that are nice to look at and can be associated with thunder and lightning, are deep convective clouds. Normally, most often they form in summer. You have solar heating of the Earth, and because our Earth's surface is heterogeneous, some bits are heated more than others. That is where the air preferentially rises. And you do see here, at this point, you develop a nice anvil, and that's your warning sign that thunder and lightning is not far away. Because what this blurry outline up here tells you that the upper part is composed of ice crystals, and they have different sizes, different weights, and fall differently, so there's a blurry outline. But down here, where you see the sharp edges, you have tiny small cloud droplets, and they hang around. They're around 5 micrometers. They just hang around there. All the same size, very well defined. And this coexistence of liquid and ice is crucial for charge separation, and is what ultimately leads to thunder and lightning. Here's a nice example, actually Austria, where some heavy downpour was an extreme. Something as short-lived as that, always a convective shower, will become more often in future because it's warmer, we have more moisture in the atmosphere, the more water vapor will condense and will come down. So you can also call that free showers if you're outside. Okay, on the microscopic level, as I said, we need the aerosol particles for the cloud droplets to form on. And they have a variety of sources. We have, for instance, sea spray if you are over the ocean. We do have Sahara dust, which is nicely visible here in this yellowish colors. And you see the yellowish color means it obscures some of the solar radiation, but not as much as the white cloud that you see here. So the cloud, if it forms, is much optically thicker, and then the aerosols are not visible. And then we have pollen, so everybody who is allergic, has hay fever, knows that this is also tiny aerosols that are around in the atmosphere. And then we get them from volcanoes, and I'll come back to that, and of course from human activity, from fossil fuel combustion or wildfires, which is a mixture of human and nature. And so yes, we have enough of that on Earth. You see what happens if you don't have enough. There's one nice example to demonstrate that without aerosol particles, you don't actually form any clouds. And this is the setup. This is like 15 years ago. It doesn't really matter. But a cold temperature outside, -8, and the aerosol concentration is only 1% or so of what you normally have. So very clean air in the Arctic. And then let's see, I think I have to start it here.
We have some hot tea here.
Hot tea here.
I'm about to stick some Earl Grey into this cup of hot water.
And there's hardly any
steam coming out.
Because there's no particles.
Want to walk inside? Want to walk inside and show how much steam is coming out?
Sorry?
You want to go inside and show how much steam is coming out inside?
Yeah.
This water is really hot. Okay, so we're going to walk inside so you can see what it looks like. How much steam is actually coming out with non-really clean air.
Oh, I don't have a lighter. Do you have a lighter?
Yes, I do.
Oh, just put the lighter. Just come, get it.
Oh, okay.
Just put the lighter above the steam.
Instead of going inside, we're just going to put a lighter over it. Look at that.
Oh my God.
Look at that.
Particles?
Particles? No particles.
No particles.
Well, why is this?
Particles.
Because lighters produce huge amounts of very small particles.
Yeah, all right.
Yeah.
So the pollution from the lighter.
Pollution from the lighter causes the fog to be formed.
Great.
Okay, so you see, if it's way too clean, you don't even get a cloud. We have enough of that, so no, don't worry, the air above Vienna is not too clean. What does it do for climate? Well, we have also some experiments that are going on that help us, or like experiments in quotation mark, because we have pollution sources. And earlier on, nowadays, ship exhaust becomes a little bit cleaner, but before it became cleaner, ship exhaust is actually one of the most bad combustion sources that you can think of. And we know we are over the ocean, so we have enough moisture, so that ingredient is there. And then you can see that if you have, imagine here you have a clean cloud where the water vapor condenses on only few particles, as compared to when you add the ship exhaust and you create a cloud with many more and small particles. The difference that you see actually in satellite images, you see here bright lines. So there is some perturbation that we are already doing to the atmosphere that you do see visible here in those bright lines, because with this water vapor being distributed over more particles, you increase the overall surface area of the cloud and more radiation is reflected back to space. So there is some perturbation there. The question is, how large is that? What have we actually done to the climate system so far? What do we see in terms of aerosol perturbation? Let's start with the clouds in the climate system. How much do they matter? Well, a lot. We tend to look at it in a global average, annual average, energy balance. What is the energy coming from the sun in terms of watts per meter square? So 340 watts per meter square coming in. You see that approximately a third of that is reflected, so and of that, a quarter by Earth's surface and 3/4 from aerosols, clouds, and trace gases. And then here, of this, what is reflected, the majority again is clouds. So clouds are, as you know from experience in summer, your natural sun screen. Your umbrella, whatever you want. The clouds are just there, they reflect sunlight. And that is actually their predominant role. But we also have high-level cirrus clouds that are at high altitudes, like where the contrast from the aircraft are, that actually act similar to our greenhouse gases. They emit with much colder temperatures, around -50, -60, the long-wave radiation back to space as compared to the radiation that you would have from the warmer atmosphere below. So those clouds here actually amplify the heating that we have. Those clouds save us, they cool. Those clouds have a higher heating impact. And also, actually, the most important aspect of clouds in the climate system is actually that there is an energy transformation from the surface back into the atmosphere. All the evaporation that you have over the ocean is put back into the atmosphere. So they are also a good contributor of water vapor, heat exchange, trace transport. So there's a lot of role of them as well. If we stick with the radiation, then we can distinguish the different cloud types. So here is some, I know it's small images, but it's a nice study that actually separates and tries to separate what is actually the radiative effect of major cloud types. And you see it's only cirrus, those are the high-level clouds that were just on the right, that basically have a positive contribution everywhere, and mid-level, altostratus is kind of a mid-level cloud. Those together are the ones that have a positive effect. And here, this is low cloud stratocumulus. You see predominantly over the ocean is where the Earth atmosphere system cools. It makes sense that this is mainly over the oceans because you have the dark ocean surface, you put a white surface on top, and you reflect much more radiation back. Then a lot of our clouds in the system are so-called multi-layer, so we can't really say what it is. On average, they also have a negative effect. When we come back to where's the aerosol perturbation coming in? Aerosol, if we look at the heating, the warming that we have of the Earth system since pre-industrial times, we are at about 1.1 degree. This is if it comes from, it depends on the reference period that you look at. It can be up to 1.3 degrees in the global mean. As I say, there's some variability. And of course, the biggest contribution is the increase of the well-mixed greenhouse gases, first of all carbon dioxide, and then methane, nitrous oxides, halogens, and so on. The only thing that is noticeable negative is the aerosol particles. And not so much the aerosol particles per se. I mean, of course, they also, just their presence reflects shortwave radiation back to space. But more importantly, here in the lighter blue, they interact with the clouds, what I just showed you from the ship track example. And so that's where we have, if you look at this in terms of temperature, have half a degree of cooling. So imagine now we didn't have them anymore because we cleaned the atmosphere up because aerosols are bad for health, and then we start to cough, exactly. We would have this additional half a degree warming. So in some sense, the aerosol, as bad as they are for health, they are good for our climate. But there's also some uncertainties, and that's why it's fun to do research about them. Okay, so I show you one example. What can we use? We can use ship tracks. We saw that example in the sketch. I'll come back to that. We can also take volcanic eruptions. And there have been a volcanic eruption in Iceland 2 months, September, October 2014, that it actually some degassing sulfur dioxide then oxidizes and forms sulfate particles later on. And here is actually, that was too quick, where machine learning comes into place. Because satellite data, we can also train now neural networks, or machine, in this case, random forest, to figure out how different cloud properties depend on each other, on sea surface temperature, on atmospheric stability, you name it. And so we have done this training for a 20-year period, but excluding the year with the volcanic eruption. And you see that with this random forest method, we got a very good agreement between different properties. So the number of cloud droplets, their size, how much water is in them, that's the integrated water content, and just the fraction, the coverage of them. Now, if we take the volcanic eruption year, then the neural network, so that's the pink, now you see the difference. No, sorry. The neural network is the black. That would still predict, because the environmental conditions, except for the additional aerosols, are the same, would still predict conditions that you see in the black line. But with the volcanic eruption in the observations, we now see a difference. And what we see now is that there are, in pink, more cloud droplets. So yes, we do see the effect from the volcano to the cloud. We see, as we had in the ship track examples, those cloud droplets are smaller. Hardly any change over on the water content, so whatever condenses more or less stays the same. But the clouds are more spread out. They have a larger coverage, and that means there's more reflection of sunlight. We try to quantify that as well, but here I show you first the regional distribution. So this is the area where here's Iceland, where the volcanic eruption was. And you see surrounding that this increase in cloud drop number with the smaller radii, and here an increase in the coverage. And the two data sets are overlaid to each other so that you do see the perturbation from the volcano here. So this increase, higher cloud drop number, smaller size, and more cloud fraction. So it seems to be a pretty consistent signal. We can quantify that and look at the sensitivity. So how much Is the cloud droplet size changed if we have more, if we have the volcanic eruption? Is there a change in the water content? What is the change in the cloud fraction? You see what sticks out is here, yes, of course, more cloud droplets, they are smaller, and we have this increase. And this is actually interesting because climate models traditionally tell you something else. And climate models are those that we use to project to future climate. Climate models would tell you there's an increase in liquid water and no change in cloud fraction. So this is something that we yet have to use to improve our climate models. Yes, this is exactly what I just said. Interesting enough, there came a study out also using the same satellite data just 2 days ago. They did something similar in looking at the ship tracks again. And what they found from the ship tracks here, the Toomey effect means that you just have the decrease in cloud droplet size. And you see this is predominantly there where you have lots of ship tracks, is where we have our marine stratocumulus areas. There's where they see a large change. Here, in terms of liquid water, the study has positive and negative signs. Overall, this is a small signal, but cloud fraction, the same what we had from the hole-around eruption, is also everywhere an increase in cloud fraction. So that's definitely something to challenge our climate models with. Overall, the magnitude is still the same as what other studies had, around 1 watts per meter square. That's approximately this half of a degree warming that we have seen before. So the conclusion is the same here. They actually said this increase in cloud cover is 50 to 300% as compared to this effect that you have up here. So it is definitely something we need to understand. Okay, with this, let me switch to the future and the most controversial topic that we have in atmospheric science. I have shown you, demonstrated you aerosols and some cloud types, cool. You're all physicists. You would say, well, what could we do to actually change climate? Either we get more of those reflective clouds, or we get rid of those clouds that warm, right? That would be the easiest. Hopefully with no other harm to the environment. Well, it actually, climate scientists started to discuss that because Paul Crutzen, some of you may know, he was a Nobel laureate. He was the first to say, well, Earth is warming, couldn't we do something against it? I show you the method that he proposed as well. But how is the situation looking like? It's warming. The 1.5 degree target has been reached at least for 1 day already this year. So we are getting there. We are getting towards the 2 degree warming that was set in the Paris Agreement, especially if we continue without any efforts, we continue linearly on this line. If we are good in mitigation, so reducing CO2 emissions, greenhouse gas emissions, it will help a little bit, but it will be very slow. We can also take CO2 out of the atmosphere. There's also some approaches suggesting that. Problem with that is that most of them are use a lot of energy, and that's not what you really want. But it will ultimately be needed to get rid of the CO2 that we have put in. And then the idea is, well, maybe temporarily, couldn't we just modify the energy budget that I've shown you? Couldn't we make clouds more reflective or get rid of the ones that warm? That could be a temporary solution until a time where that's not needed, because mitigation and carbon dioxide removal have gotten us to a temperature where that's actually decreasing again. So yes, how would we do that? Increase those, get rid of those. That would be the very easy way to say that. Well, I talked already about a volcanic eruption. Volcanic eruption does something of that naturally. it actually cools, as I'll show you in a second. So one idea would be to more or less do that artificially, trigger volcanic, no, not trigger volcanic eruptions, but mimic the effect of that. Or the alternative is, if we are over the oceans, we could just make brighter clouds. We could actually have something that is wind-driven, powered, goes over the ocean, releases some of the sea spray, just have to ensure that the sea spray reaches the clouds, and that would be a cleaner way than what we have seen from the ship tracks, would also be possible. Or something trying to get rid of the cirrus clouds. Blaž here, who is in the audience, he is the expert on that. He did that while he was a PhD student with me a while ago. So there the idea is, if you think of that, this is a natural, normal cirrus cloud, and here you now do the opposite from what we have seen in a ship track. So here you have to imagine a cirrus cloud normally consists of very small crystals, that's why it's hanging there. So if you were to get it to form at lower altitudes on a few larger particles, then those ice crystals would sediment and the cirrus cloud would be gone. I'll show you in a bit if it works or not. Or you could bet. Is any of those methods working? Somebody raising hand. Is any of those methods working? Only one. You're right. All the other dare not too much to say that, I think. But yes, so the volcanic, starting with the volcanic eruption example, that was actually Paul Crutzen's idea. Because he knew that if you have a deep volcanic eruption that goes all the way to the stratosphere, so maybe to 20, 30 kilometers high, up there is no clouds anymore, so the removal of those aerosol particles by clouds is just not there. The sink is absent, so they can only come down due to their own weight, come down by gravity. And that takes rather a year or so. So if you inject a sufficient amount of sulfur dioxide into the stratosphere and you form sulfuric acid particles, you reflect sunlight, and then down here is the cooling. The last big example that we could study as atmospheric scientists is unfortunately over 20 years ago. That was the Mount Pinatubo eruption in 91. And there, what you see here is like the three thick lines are different estimates of temperatures from observations, and all the yellow lines are different climate models. We see this pronounced dip just after the volcanic eruption, and then it takes around 5 years or so until we are back to more normal conditions. And so the cooling that you have, depending on the estimate, it was also overlaid with some natural variability. If you get rid of that, then it's approximately ½ a degree in the global mean. So Paul Crutzen's idea was then to say, well, we should artificially inject those sulfur dioxide particles into the stratosphere. And scientists have been thinking about that ever since. There has been one study that looked rather promising that said, yes, here, this is the top of the atmosphere forcing, so the radiative effect, you can approximately divide that by 2 to get temperature in cooling. If we just inject more and more and more, we do get more and more cooling, so this would actually be a solution forever. So you get a cooling of, I don't know, -5 degrees or something like that. And you see it's not linear, it's leveling off, because the more material you inject, the easier it is for the particles to coagulate, then they become larger and they sediment faster. Well, what that means in terms of emissions, if you were to compare that to the year 2000 sulfur emissions, then it's approximately 2/3 of that you would need to counteract actually a business as usual climate change scenario by 2100. But this looked like at least it's possible. And then there came in US studies that said, forget about it. This coagulation effect is much stronger. And the particles that you inject, they tend to stay in the same region. They don't spread out globally as much. And there's actually a sweet spot. And what you achieve is not approaching 10 watts per meter square, but less than a fifth of that, 2 watts per meter square, so maybe a degree of cooling. But at least temporarily, it could do something. So it looks like, yes, if you do have higher injection rates, we know that there's faster coagulation, particles become larger in sediment, so it's not. This is what more people these days say, no, this is not an unlimited method. Okay, then we can come to the next idea. Ship tracks. We have seen this example, how it works. You can either do that from ships or some other method that you have. And here were some model, around 10 different climate models simulating that for around 50 years. And then at this point, the simulations were set up in the way that at 2070, it stopped, and you see that it quickly goes back to normal. What you see here, that's around the same order of magnitude what I showed you from the stratospheric aerosol eruptions, approximately 1 Kelvin reduction that you get in the mean, and you see a big difference between the models. The interesting thing is, though, this is one of the methods that actually currently used and tried out, and that's locally. That's locally in Australia because they want to protect the Great Barrier Reef. They don't want to see much. They have their corals bleaching there. And of course, as long as coral bleaching is also related to warm water and to the CO2, the acidification of the ocean doesn't help. But at least the idea was that they could try to prevent some of it if regionally they just made their clouds brighter and got less sunlight into the ocean. And there's actually, there was an opinion paper in Nature, I think. And nowadays, it's also the Australian government is figuring out how to do that, but that is an approach that will at least be tried out regionally. Cirrus clouds, depending on the source that I showed you, they do have a positive radiative forcing so that they lead to some warming. It depends on the source, if it's 2 watts per meter square or 5 watts per meter square. So then you can imagine if you got rid of all of them, you would have a cooling of approximately 1 to 2.5 Kelvin or so, if it was successful. This was the slide. Now I explain you a little more in detail how this would work. The reason why you do see contrails in the sky is very often up there, you do have enough water vapor, but there is nothing to condense on. So actually with a contrail, it's a different method. There you emit some additional water vapor and you cause some large cooling from the turbines, but that's a different story. But just to show you, to tell you, depending on if you see a contrail or not, depends on the moisture. So there is moisture, and the idea here is that if we include some particles in the atmosphere on which this water vapor could form, and zwar lower down in the atmosphere where there's more water vapor, the crystals would grow larger and then they would sediment and also get rid of the water vapor, which is a greenhouse gas. So that could lead to a cooling. Tricky thing is, I don't think I would know, and I don't think Blaž knows, but maybe I changed his mind. I'm not sure if we are able to find the locations in good time to remove the water vapor and don't run into the problem of just creating more cirrus clouds. This is the first study that looked into that around 9 years ago. And what is shown here is watts per meter square. And this is a function here of how many of those ice nucleating particles are injected into those cirrus levels. And you see that the study found it depends. There is a sweet spot, approximately 20 per liter, which is a typical number that we could find in the atmosphere. Otherwise, you actually do get a negative forcing, so that's actually what you want, a cooling effect. But if you inject too many of them, it's an overseeding. You make the cirrus cloud even optically thicker. And that's definitely that's definitely nothing that you want. So there's also a problem here that it can't be too many of them. But then Blasch tried that with our model, and the results that he reached was similar to another study. So I was sorry, with our climate model, we don't even get any cooling. We get overseeding right away. So this method is amplifying warming rather than doing anything else. But then he made the particles really huge, and then I'm not sure how much material you would need to get up there, but at least then it worked. Then I tried with one more PhD student until I've really stopped this now. And he basically used a more sophisticated way to look at the different processes inside the clouds. And those are those two last lines here, and you see they are only positive. So the conclusion is, if you didn't raise your hand because you didn't think it works, cirrus thinning really doesn't work. So that's not a method to rely on, if you ask me. And then there's one last one to tell you is maybe we should look at some clouds that are a little bit, I showed you there's not only warming of those cirrus clouds, but also some of the clouds one level below, they also warm. So here, those alto stratus clouds. Not so much in the global mean, but regionally a bit. And if you look at that seasonally, then in high latitudes, maybe there's actually some potential for high latitudes. Because so here in red, you have the northern between 60 and 80 north. In wintertime, you see that the cloud radiative effect of these clouds is actually positive here and here. And on the southern hemisphere in blue, the opposite also in their summer, it is positive. So if those clouds you would able to remove in the winter when there's only the long wave effect, so then they don't reflect any sunlight, but all they do is keeping the long wave radiation that's emitted from Earth within the Earth's atmosphere system. Here, physics. Back to physics. Physics on a very detailed level. This method has a better chance of working because we know that the saturation vapor pressure over ice is lower than over supercooled cloud water, liquid water. So if you do have, and one of the reasons why those clouds are persistent is because they are at temperatures below 0 degrees. They consist of supercooled liquid droplets because there's no aerosol for the ice crystal to form on, the lack of a crystallization site. But once you have that, you see that this crystal grows at the expense of the evaporating cloud droplets. The nice example of that you sometimes see in the atmosphere is so-called hole punch clouds. We actually see this visually all around it is supercooled cloud droplets. And here, this was an aircraft doing it, inducing some temperature degree that you really got some freezing. The minute you get ice crystals to form, you see they quickly grow large and sediment and create a hole in the cloud. So that would be a method that could potentially work. And so Diego Villanueva, who did this study, he basically looked at the effect, cloud radiative effect. If you can basically get some cooling over the Southern Ocean or the Arctic Ocean, depending on how many ice crystals you put in, if you limit it to the respective winter season on that hemisphere. And then he looked also what would that be in terms of a regional temperature change. So here for the Arctic, one sector in the Arctic, and here for the Southern Ocean. And that's locally in that region that is highlighted in green, a temperature change of around 0.5 degree to 1 degree, and some restoration of the sea ice. So maybe there's another thing that could work, at least regionally, a little bit. With this, I'd like to wrap up. I hope I've shown you that in order to understand clouds and precipitation, it's also worthwhile to look in the lab microscopically, or actually what Bernadette is doing, take aircraft missions and really understand the distribution and the properties of those aerosol particles much better. And then what I've also shown you is the clouds do both things. They help us to reflect sunlight as they do today. Not that that would be too much in November anyhow, but they do. And they have also some warming effect. They keep some of the terrestrial radiation within the Earth atmosphere system. Aerosol-cloud interaction remain to be not fully understood. Climate models yet cannot reproduce what observations are telling us. How much cloud water increase should we have as compared to cloud fraction? We don't know that yet. And so far what I've shown you, climate intervention methods in theory work. I don't think there's anything that is scalable yet. Of course, it won't cure the problem. Acidifications of the ocean continues. And there's other side effects like precipitation areas are shifted. And we have seen what it can do, some flooding or droughts. So it's lots of problems associated with that. But there is different, at least us scientists have tried to think about it and try to at least explain what it could be do or could not do. And with this, I'd like to thank you for your attention. I'm happy to welcome questions.
Thank you very much for this very interesting presentation. I think there's questions. Yeah, Regina?
Yes. Well, actually, my questions are rather technical. What is the reason that the second Toomey effect was not included in the models?
It is included. It's just that the climate models are simple. They basically tell you the more cloud droplets you create and the smaller they are, the less they form precipitation. And in climate models, that causes a buildup of cloud water.
Yes, but I mean increase of cloud cover.
Yeah, that's because
in 77.
Yeah, that's because the cloud models most of them have a simple way to prescribe cloud cover, and that is that they relate that just on relative humidity. And as long as relative humidity is not changing, also the coverage is not changing. And then they additionally, yeah.
And the second question is, with this zero seeding, did the models also take into effect the multiplication effect?
Ice multiplication, there's not so much the secondary ice production that you are alluding to. It's more what?
Fragmentation of crystals.
Yeah, but that is ice multiplication. Yes, that exists. We know from some lab experiments in which temperature ranges that works. Normally that's limited to warmer temperatures. It's nothing that you see in cirrus clouds where you have typically rather small and isolated ice crystals and they don't get into contact with each other.
There was a question in the back.
So I'm not an expert, so you may excuse possible naivety in question, but it seems to me that these models that you showed us, various plots and graphs and so on, obtained by various generations of students and so on, it's strongly data-driven, and it is mostly not from first principles. So it is a lot of empirical modeling and work is there. And then it is crucial, I understand, from your talk, that we should be able to quickly, quantitatively predict changing basic hypotheses of certain feedback loops that we believe are there or are not there. So could it be done by AI? I mean, what role does AI play in just sort of exploring the feedback loop space that could be active given a certain amount of data? And could AI suggest, let us say, most important additional data acquisition that you would need to make a hypothesis either supported or refuted? Can you comment? So it's more
yes, we are discussing it, of course. I mean, we are also thinking of how to include AI, what could be done. If some parameterizations that are empirically based could be replaced by AI. But what we try to do with most of our approaches, we let them guide by physical principles. So like, for instance, all the cirrus formation is based on classical nucleation theory. There's a theory behind it. There's nucleation theory behind it. And we know how it changed in the presence of a foreign particle. So that's all physics. What we don't know is actually how the particles in the atmosphere look like. So if you approximate them, say, by their contact angle or something like that, you don't know exactly what the contact angle distribution is that you have in the atmosphere. So yes, AI will definitely be coming in different ways. I think we are a little bit hesitant to replace too much of it with it, but there is this mixture of physics-based or physics-informed AI that you could still do. And so wherever we have our physical theory, then we don't lose that.
Thank you.
More questions?
So a naive question. Can you say a word about the models you use to make that?
Very different ones. We use the global climate models that we use that I showed you for the climate projections. They have still rather coarse grids, and then lots of the processes need to be empirically described or parameterized with what we have on the grid scale available. They still have grids on the order of tens to hundreds of kilometers, so really coarse. But then we also have something that we call large eddy simulations that simulate the turnover in also closer here to the surface, and that they can be as small as 10 meters, or normally we go to 15 meters, something like that. And then resolve at least the motion that lead to cloud formation much better. Very different skills.
One more question?
Wouldn't lead putting sulfur into the atmosphere to acid rain like in the 1980s?
It depends on how much you put in. The amounts that it is some question if therefore that is the best material. People have also thought about maybe you could replace, if you put it in the stratosphere, with some other material, like more like mineral dust or something like that, that wouldn't have that effect. That is something that you would find in deserts or something like that.
There was another question in the back.
Yeah, I've seen different model of the simulation can lead like completely different outcome in the future, no? And in order like that, a government, like say, accepts like a sort of like reaction to the climate change. I think also like an error estimation, it's very important, like to keep track of the behavior and how one can given a model infer like the errors and the spreading of the possible outcome. I think it's very important to...
Yes, I mean, possible governance of solar radiation management will be anyhow a very tough problem, because it would be, if you want to have a solution that's global, every country needs to agree upon, because, and there are some who may not. So if you think from a biodiversity aspect, maybe you want to save the Arctic sea ice, but there's economic interests that prefer to have a free Arctic Ocean for economic reasons. So you will have that struggle anyhow. So it's not easy. I think Australia can explore it because clouds are really local, and I mean, the lifetime of those aerosols is a day or so. So if we want to revert it, no danger done, and there's no other continent or no other country next to it. But if you do something like stratosphere, where it only matters if you have a global effect, that's a huge governance issue.
There was one more question here.
Concerning governance, in Germany, I observe in science funding institutions sometimes a competition between scientists asking for money for modeling computers and scientists asking for money for data acquisition. How do you see this balance? Are these two groups of scientists really working together and having a joint strategy between theory and data acquisition, or is this an unhealthy competition?
Well, you don't get any advances in any type of modeling if you don't work together with observationalists. It doesn't work, because only if you take observations do we learn something about our atmosphere. So yes, they should work together. I'm not sure what happens in Germany. Luckily, I can't comment on that too much, but they should work together.
I think I have one last question, and then we have to go to a coffee break. This September was very unusually hot, and there's discussions that aerosols could be the cause, that there was new legislation put into place that ship emissions are not as bad as they have been in the past. Can you comment on this? So
the ship emissions, how important ship emissions are, is also a huge topic of debate. It ranges between that the estimates were from it is in the milliwatts to say half a watt or something like that. So if you convert that, then maybe there's some warming getting out of that. I don't think it's just the ship emissions. I think it has more to do with that we are entering an El Niño phase again, and that's natural variability that's at the moment doing it. But yes, of course, cleaning up. As I said before, if we clean up the atmosphere, it gets warmer because of that. So that is definitely true. So if we clean up the atmosphere at the same time, we have to reduce greenhouse gas emissions at the same time in order to avoid an increased warming to have.
Thank you very much for these very nice insights. Do you want to?
There is coffee break now, and we will do it at 11, but we should first.
Thank you so much.